Hello. This is going to be an overview of some of the videos I've made picking up in the history of bird evolution from the Jurassic period and the first birds. And so theropod dinosaurs had evolved a diversity of lineages. So within the theropods, then there were the tetanorans. Within the tetanorans, then there were the theropods, etc. And so it was a nested hierarchy. And at each point, there were some of the features which define birds, which evolved in dinosaurs. And so there were all of these dinosaurs which had some, but not all of the features of birds. And so that if you were to look up in the air during the early to mid Jurassic period, you would have seen dinosaurs that looked like birds. And then you also would have seen the first birds, but they then had many of the features of dinosaurs. Now, the best known and most famous example is Archaeopteryx. There have been a few other fossils. There was one in Texas, Proto-Avis, which some advocates claim was should be a candidate as one of the first birds. One of the difficult things is that the dinosaurs were so much like the birds, some of them in the Paraves group, that who crosses the line? Where is that line that defines bird? Because the first birds still had grasping, clawed fingers. Yes, they had wings, but at the tips of the wings, they had fingers which they could use to grab things. They still had teeth, the way that no modern bird has, although I'll get back to that later. They had a long reptilian tail. They lacked the features which define the birds, like the thorax, the keeled sternum, the modifications of the shoulder. These early birds, like Archaeopteryx, are certainly defined as birds, but they have all of these dinosaurian features. Now, why is this a bird while something like Microraptor or Anchiornis isn't, even though they had feathers, and some like Microraptor and Rahona could arguably fly? Well, at some point, just the way that we use words, we have to define it. And, you're a bird if you have these features, you're not a bird if you don't. So what crosses the line? That's really, tough. One of the few things is this toe, that in many dinosaurs, this first toe was reduced. In many dinosaurs, it had started to face more backwards. But the idea that it is truly retroverted, so that it faces the forward three, so that you could actually perch on a branch, that is something that the other theropods don't have. They're close, but they don't have a true perching foot. So that if you're looking for a feature that says, here's the line, you could also then say the length of the arms, but that's kind of like a percentage. So that, like, as you went through the theropod family tree, the arms were getting relatively longer, relatively longer, relatively longer. The longer they got, the more efficient they would be as a wing. But it wasn't like a qualitative feature where you have it or you don't. It was just, they were getting the ability to potentially glide and potentially that would be better at flying. So these are true transitional fossils then, in that just as the theropod dinosaurs had some but not all features of the birds, these early birds have some but not all features of the theropod dinosaurs. It should also be noted that while the typical theropod hip had a pubic bone which went forward, in the last group of theropods like Velociraptor and Deinonychus and others, this had started to move more posteriorly. And so not only in the theropods, but then also in the birds, the pubic bone is oriented differently than in most theropod dinosaurs. All right. So then by the Jurassic period, there are birds for the first time. There were 0 birds on planet Earth during the Precambrian, during all of the Paleozoic, during the Triassic, as far as we know, unless, say, Proto-Avis is a bird. But now by the mid-Jurassic, there are birds. But by saying that, they are certainly not modern birds. There are no blue jays, there are no crows, there are no hawks, there are no ducks, there are no woodpeckers, there are no owls. None of the modern groups of birds are present. And so the earliest birds have all of these primitive features like the teeth, the clawed grasping fingers. One of the first features which will be modified in these earliest birds is this long tail will be reduced. Apparently, if you're going to fly, having that long, heavy tail, that is one of the first things that natural selection acted on. And so the tail of birds was modified to form what's known as a pygostyle, where a bunch of vertebrae at the tip fuse to make a solid bone to which tail feathers can be anchored in, say, a fan. So the earliest birds had, say, a frond-shaped tail, elongated with feathers going out along the edges, whereas modern birds have a fan-shaped tail where it's short with a solid bone at the tip. And so there are a few birds which are known with this frond-shaped tail, but then one of the first things which would occur is, once again, the reduction of the tail to form a pygostyle. And so then there were clawed, toothed birds, which were more advanced than the very first birds because they had a pygostyle, and that modified a tail. So that would be one of the first changes. To evolve in birds. And so, just as in the previous video, there is a family tree where one sees traits developing slowly. So let's just look at that for a second. So the features that make modern birds, some of them were present in the first birds, but not all of them. The first birds were not good flyers, and they lacked many features which define modern birds. These would evolve slowly. And so when we look at birds, they certainly didn't appear fully formed. Instead, over tens of millions of years, they slowly evolved. So in the very first birds, there was once again that first toe was more reversed. They had a longer hand and arm. The flight feathers were asymmetrical. So we'll see feathers in a little bit, but that means if you look at the central shaft, the rachis, that the barbs which go off to the sides are kind of more compressed on one side. And that is an adaptation for flight. So now you could argue that these feathers are not being used for courtship or display, but actually for flight, because the shape of the feathers is adapted for that. So those are features which appeared in the first birds. And then within the group of birds, then there's that group Pygostylia. So now some of the birds reduced their tail. A horny beak apparently comes later, where now there are no longer teeth at the very tip of the tail. And then this continues. And one of the major changes is in the Cretaceous now. There's a group called the Ornithothoraces, that modified the thorax. So this was, a major thing in the Mesozoic. And so compared to the first birds, the chest and the shoulder region of the birds was modified. So unlike the first birds, this group here, the Ornithothoraces, had a whole bunch of features. So, okay, I'm sorry. That's in this other. So let me just go through some of the changes of the thorax. First, bird ribs are different in a number of ways. First, they have these processes which help to reinforce the thorax so that they can contact each other and anchor more muscles so that they can better withstand um, the forces of flight. Birds have sternal ribs. Not only do they have ribs which go down from the vertebrae, but they also then have these sternal ribs which go up from the sternum. And so here you'll see both the normal ribs and then the sternal ribs coming up from the sternum. Now this is an alligator, and notice that you have some cartilage pieces in reptiles, but these are these become bone in birds. So you have these uncinate processes here which are strengthening the thorax, making it better for flight. So there are these changes in the thorax. The first, another change that the ornithothoraces birds evolved was they changed the sternum, the breastbone. Now, birds can fly, and actually not only can they fly, they can take off from a standstill. So if, say, birds are outside your deck and you open a door, they can just whoosh and they're airborne. So unlike humans, which have a flat sternum here, which attaches our chest muscles. Now, our chest muscles can be prominent, but they're attaching to this flat sternum. What the ornithothoraces group evolved was a keel on the sternum, which then allows a greater muscle attachment site. So if you look at the size of the sternum, which projects out to here, this means that the chest muscles, can actually be huge, as you know, from, eating chicken or turkey. And so unlike the very first birds, so this was not present in Archaeopteryx and the earliest birds. But then later birds developed this keeled sternum, which would give them so many more flight muscles and allow them to take off at a standstill. Some birds like Confuciornis, had a small keel, but then by the Ornithothoraces group, look at the size of that, which would allow for enhanced chest muscles and thus taking off from a standstill. But then there are some other changes. So let me also then go through the shoulder. Like the dinosaurs, birds have a strap-like scapula. I apologize for the internet being so slow today. No, come on. So the dinosaurs have this strap-like scapula. It looks very unlike our scapula. So if you're thinking of your shoulder blade, dinosaurs and birds, it doesn't look anything like that. And so there's this strap-like a scapula. And the one ingenious thing, and I apologize, I'll do these videos as they pop up. It's being difficult. The ingenious thing that evolved in these birds is that there are two chest muscles of importance. The pectoralis major, which is the muscles which allow for the downstroke. But then how do you pull your wings up? Well, it would make sense if you then put the muscles here to pull the wings up. But apparently that would make flight harder because now you've got this weight above the center of gravity that would make life difficult. So one of the ingenious things about birds and their anatomy is that the muscle which pulls the wings up, called the supracoracoideus, this is the homologue of two of the rotator cuff muscles that we have, the supraspinatus and the infraspinatus. This muscle is here beneath this center of gravity, but it still manages to pull the wings up And the way that it does that, this pink supracoracoideus, which is underneath the big chest muscle, so the big pectoralis major, which is pulling the wings down, that is here in red. Underneath that is the muscles which pull the wing up. Well, how can they manage that? Well, it's because their tendon then goes up and around the scapula through this hole where three bones meet. So the scapula, the procoracoid, and then the two clavicles, which have fused to form the furcula, what you might know as the wishbone. This then forms a hole that the tendon goes through. And so a muscle that is beneath the center of gravity is actually the one that goes up and around and is pulling the wings up. So that is a change which was made in the group of birds called the Ornithothoraces birds. And this then would have allowed them, say, to take off from a standstill. All right, and so you've got this keeled sternum, you have this new modification where here in this hole, this triosseal foramen where the scapula, the procoracoid, and the wishbone, the furcula meet, that's where the tendon goes to pull the wing up. And so there were these modifications primarily in the chest of the these birds, which then made them much more efficient flyers. Along the way, just a few other things. The center of gravity was changing. So they lost their teeth. All right, birds kept their teeth for a while, and teeth were lost separately in different lineages. But the reduction of the teeth meant that there wouldn't have been as much weight going forward. Pulling the supracoracoideus and putting it beneath the pectoralis major, the muscle for the upstroke, that would have meant that there wouldn't be as much weight here. Birds, instead of chewing with their teeth here, they now have a gizzard which grinds food closer to the center of gravity. And so birds were modifying their bodies to make them more efficient for flight. And somewhere along here, I talk about the gizzard as being, where you can grind food. So, the beak was becoming toothless. All of these muscles was changing. So the center of gravity was just now in a better position to allow flight. So once you have these birds, which are not just flying birds, but good at flying, right? So the first birds were probably not all that good at flying. But then the Ornithothoraces group, they were, now very good flyers. At this point, there are two lineages of birds in the Mesozoic. There are the birds leading to our group, what's called the ornithurine birds, but they're not the major ones. So this was a surprise. It was thought that once birds evolved, they would be on their way to evolving hawks and herons and ducks and all of the modern birds, but that wasn't the case. So in the Cretaceous, these Ornithothorace birds form these two lineages. The ones which we have alive today, they were the minor group, right? So they have all of these new features. They have fusions of bones, making a carpometacarpus in their wrist, a tarsometatarsus in their foot. But then there's these two lineages. The major lineage is the opposite birds, the enantiornithine birds. They're called the opposite birds because the way that their feet bones fuse is opposite of what we see in modern birds. This was the group which then dominate in the remainder of the Mesozoic. They are the most common birds in the fossil record. They are the most widespread birds in the fossil record. Other than Antarctica, they are known in all continents. Some are sparrow-sized, some are vulture size. Some lost their teeth, but most still had their teeth. Most had fleshy tails. Some were flightless. Some had scale-like feathers. So they were quite a diverse group, these enantiornithines. And they were doing wonderfully. But then the mass extinction event at the end of the Cretaceous period not only kills off the dinosaurs and so many other groups, it also kills off the most common birds of the Cretaceous period. So the enantiornithine birds were the most common and successful group of the Cretaceous period, but then they have become extinct at the end of that. And then this other group, the euornithine birds or the ornithurine birds, they had been the minor group, but they are the only ones to survive that mass extinction. And so then they then become the ancestors of the birds which are alive today. Now, they had diversified this group a little bit as far as we know. So there were a number of diving birds which still had their teeth. Some actually lost their wings. In this group, before the end Cretaceous extinction, there's a bird which reminds us of seagulls. So it was flying, but it still had teeth. So some of the opposite birds had lost their teeth before the member of this group. So in the Cretaceous, they still retained their teeth, and there were a series of changes as time went by. They had a horny beak at the tip of the jaw, and so somewhere in this group there are members that survived the mass extinction at the end of the Cretaceous. Now, we think that at the very least, there was the distinction between two lineages before this Cretaceous extinction: the old mouth birds, the Paleognathus birds, and the Neognathus birds, which I'll get back to in a second. But let me just sum up that previous statement. So when you look at the Mesozoic, birds appeared in the Jurassic, but they were not formed the way that modern birds are. And so what happened over time is, once again, a nested hierarchy of groups within groups, so that birds got better over time. More of the traits which we associate with modern birds evolved over time. And all of these Mesozoic birds had some, but not all, of the features of the modern birds. Now, the claws on the fingers were being reduced, and the wings were changing before I get back to the modern birds and their phylogeny. I just want to show you that the bones of an arm are the same bones as the bones of the wing. So what happened over the Mesozoic is simply the arm bones were modified, and you can see the homology. There is one discussion that we could have where there's a bit of a discrepancy, is that the theropod dinosaurs had these three fingers, 1, 2, and 3, which they used in their hand. The first birds had these fingers, 1, 2, and 3, which they used in their hands. And if you were to look at the wings of a modern bird, which bones are the stubs which are fused together? Well, you could answer this one of two ways. One, it certainly looks like fingers 1, 2, and 3, which is kind of what you would expect. However, embryologically, it seems to be 2, 3, and 4. And what seems to have happened is that in the forming embryonic, wing bud, that the embryonic stem cell region forming digit 2 uses the genes for digit 1. So even though it's structurally forming in the regions of 2, 3, and 4, that they're now changing which genes they're expressing, so that they're now expressing the genes of 1, 2, and 3. And so I prefer not to get into this, because if, you know, they kind of start off as 2, 3, and 4, but they're expressing genes of 1, 2, and 3. Which ones are they? But in any case, they were the homologous bones. And there was that one little allula which can form here, which just helps kind of landing and steering at that point. Now, the digits have lost their claws, but there are exceptions. So, for example, if you look right there in this southern screamer, this shaha, they still have claws. So there were fossil birds, even in the Cenozoic, which had claws, and there are modern birds which still have claws on their wings. So here's a rhea, and you can see that there are claws. Once there was a dead emu by the side of the road, and I ended up, dissecting it, and there were these tiny little claws that you couldn't see because they were covered by feathers, but you could still see them under the wing. And I've read that there are a number of birds that still retain the remnants of claws. So big picture that these are the same bones as were present in the arm that make up the wing, but they were modified and they fused together to form a carpometacarpus. See, there's all these separate bones, but they fused together to make a carpometacarpus in the modern birds. And so I have videos on wing muscles as well. But then just moving along, if you were to look at the skulls of a rhea, an ostrich, an emu, or a few other, the bones in the roof of the mouth lack some of the features found in most modern birds, and their state is that it's more like that of reptiles. And so you could call these birds the, quote, old mouth birds, or the paleognathous birds. This seems to be the most primitive group of birds alive today. Now, while most are birds which can fly, can't fly today, they do have some flying relatives in South America today. And so here we see a relative, a paleognathous bird that is capable of flight, which is different from the majority, because things like emus, cassowaries, etc., they can't fly. And so here I just go through some of the features which mark the old mouth birds compared to the majority of birds alive today. And once again, these are the features which define the most primitive group of birds alive today. And so we can still see a number of features. So for example, in this emu pelvis, you can still see how long the ilium and the ischium are, and I go through some of the features here that define this group. We can't be sure, but we think that this division, which produced, the emus and those other lineages, we think that they had evolved by the end of the Cretaceous period, and so that of the birds today, there were actually multiple lineages which survived the end Cretaceous extinction. That's kind of like a big question among, when we consider the bird lineages. Was there just maybe like one pregnant female bird that survived the end mass extinction that was the ancestor of all modern birds? Or did a couple of lineages survive? It's hard to say. The fossil record, especially with bird fossils, which are so small and delicate, can be debated. But the best answer seems to be that it seems like a couple of lineages survived the extinction. So we think that the division between the old mouth and new mouth birds, that had occurred prior to the extinction, and so that then at least those two lineages would have survived, so that by the end of the Cretaceous, when that meteorite hit our planet, probably the ancestors of rheas, ostriches, emus, and the old mouth birds had already split. So the Paleognathus bird lineage was probably already separate by the end of this Cretaceous extinction. And so they are represented today primarily living on the South American continents. And so I go through, I'm sorry, the southern continents like Australia, Africa with ostriches, and South America. So I go through these old mouth birds, most of which are flightless. But once again, there are the tinamus of South America, which are flighted, signifying that they weren't all flightless here. So that seems to be the most primitive lineage of modern birds. And then if you were to ask, what's the next most primitive group, we could argue over loons and loon-like birds. Certainly one of the big branches then seems to be the gallo-anseri, the branch which will lead to both chickens and ducks. So it seems that chickens and ducks form a lineage that splits from the neognathus birds, the new mouth birds, at an earlier point than all of the other lineages. And a question that we could ask is, when did the branching occur? Did it occur after the end Cretaceous extinction, after the dinosaurs went extinct, or did it occur before? So the same way that we asked that for the old mouth birds, the Paleognathus, we could ask it for the gallo-anseri. Did their ancestors branch before the end of the Cretaceous or after? And the answer seems to be before. So it seems to be that the bird lineages alive today had already branched a bit prior to the end of the Cretaceous, before this extinction occurs. There are fossils which are thought to be duck-like and loon-like during the Cretaceous. And so this seems to be the model which is best supported by the fossil and by the fossil record and genetic comparisons. So then everything else in the bird lineage seems to then have come in the last 65 million years. So most of the birds and groups of birds we see today are rather new. Dinosaurs never saw them, and so they evolved in the absence of dinosaurs. So the dinosaurs become extinct, the opposite birds become extinct, and so that's when most birds diversify. Interestingly, a number of these early bird lineages seemed to, at least at first, have adapted a great size, because while mammals would become dominant predators in cats and dogs and lions and the like, for a long time, it took mammals a while to evolve these lineages. And so right after the Cretaceous extinction in the Paleocene, it seems that birds were the first group to adapt to the absence of the dinosaurs. And so there were birds which were 6 feet tall and 9 feet tall and taller, which were dominant predators. Some had horse-shaped skulls. They weren't that closely related to each other. And so this was an example of different bird lineages in different parts of the world, now just adapting to the absence of large dinosaur predators and increasing their size. So they've been nicknamed the terror birds, but what they didn't really form a group of related birds. And these would include the And so among the ones which had great size would include some like moas and elephant birds, which were still alive on islands like Madagascar and New Guinea in historical times, but which were forced to extinction by humans. During the last 65 million years, bird groups evolved one by one, and I give some as some examples. And so before there were um, modern woodpeckers, there were birds which have some but not all of the features of woodpeckers, and there are still piculets alive today. Before there were modern penguins, there were birds which had some but not all of the features of penguins. There were long-legged hawks, which predate the hawks and eagles of today. And the most common birds today, these songbirds, these small birds which have a syrinx, which allows them to make sound, they actually seem to be the last group of birds alive today. And so if you were to look at a bird family tree, the songbirds, which are the most common birds alive today, they are the last to evolve. And so birds certainly did not appear all together when the first birds existed, nor did birds appear in the Cenozoic, in the modern groups. They evolved slowly. And so throughout the past 65 million years, we've seen group after group of the birds alive today, with the most common birds, the songbirds, being the last to evolve.